All right, welcome to The Explainer. Today, we're diving into one of the biggest stories out there, the life of a star. From, the total darkness of space to the blazing heart of a sun, we're going to trace that whole epic journey of how a star is born. So, let's get started.
I mean, it's a question we've all asked, right? You look up at the night sky and wonder, what makes a star shine? Turns out, the answer involves some of the most powerful forces in the entire universe. It's all about turning basically empty space into this brilliant, light-giving engine.
So you might be thinking of some huge, explosive beginning, but that's not how it works. The birth of a star actually starts in the quietest, coldest, and darkest corners of a galaxy. We're talking about these vast, almost serene clouds of gas and dust.
Okay, so our first chapter kicks off right here, inside these cosmic clouds. This is where all the raw ingredients for making stars have just been hanging out for millions of years. This is the story of how that dust starts its journey toward its destiny.
So the place where all this happens, it's called a nebula. And you can really just think of it as a cosmic nursery. These things are enormous clouds, sometimes hundreds of light years across, and they're made of pretty simple stuff, almost entirely hydrogen and helium, which are, the two most basic building blocks in the whole universe.
Right, but here's the thing. These cold, stable clouds, they're not just going to collapse on their own. They need a push, a little nudge, a cosmic kickstarter, if you will. And this could be anything from the shock wave from a nearby exploding star, a supernova, or even just two clouds kind of gently bumping into each other. Basically anything to give gravity that tiny little advantage it needs to finally take over.
So once that trigger happens, a dense pocket inside the nebula starts to collapse in on itself. And as it shrinks, a really fundamental law of physics kicks in. Gravity starts converting the cloud's potential energy into heat. So the core begins to warm up, and pretty soon you've got this glowing baby star, what we call a protostar.
Now, this protostar just keeps pulling in more and more gas and dust, getting hotter and denser all the time. But, and this is important, it's not officially a star yet. For that, we need the main event. We need ignition.
And this is the magic number you need to remember, 10 million Kelvin. That's unbelievably hot. Once the protostar's core hits this temperature, the rules of physics kind of change, and something absolutely incredible is about to happen.
And boom, at 10 million Kelvin, you get ignition. Nuclear fusion kicks in, releasing this tremendous amount of energy. Now you've got this outward pressure that's finally strong enough to fight back against gravity's inward crush. And when those two forces find a perfect balance, we call it hydrostatic equilibrium, the collapse just stops. And there you have it. A stable, shining, main sequence star is officially born.
All right, so our star is born, it's shining bright. But what is this engine deep in its core that's going to power it for, in some cases, billions of years? Let's pop the hood and take a look.
Okay, it's really useful here to know the difference between two types of nuclear power. Down here on Earth, our power plants use what's called fission. That's splitting heavy atoms apart. But stars, they use fusion. They're squeezing light atoms together to create heavier ones. And trust me, it is a much, much more powerful process.
So the sun's recipe is actually pretty simple, but unbelievably powerful. Deep in its core, it takes 4 hydrogen atoms and, under all that heat and pressure, it fuses them into one helium atom. But here's the amazing part. That final helium atom weighs just a tiny bit less than the 4 hydrogen atoms did to begin with. So where did that leftover mass go? It gets converted directly into a massive amount of energy. That's equals mc squared in action, right there. To put it in perspective, our sun converts 700 million tons of hydrogen into pure energy every single second. Just wow.
Okay, so now that we have a handle on how stars actually work, let's bring it all back home and take a closer look at our very own main sequence star, the sun, because it turns out it has some pretty peculiar habits. So here's a really fascinating, kind of counterintuitive fact about stars. The bigger and more massive they are, the shorter their lives. It seems weird, right? They have way more fuel, but they burn through it at a ridiculously fast rate. It's basically the ultimate live fast, die young story of the cosmos.
And when you look at the numbers, they're just staggering. A star that's, say, 25 times the mass of our sun, it'll burn out in just a few million years. Poof, gone. Meanwhile, our sun, at a nice, comfortable 1 solar mass, has a super stable lifetime of about 10 billion years. And we're about halfway through that right now, which is pretty good news for us.
You see, unlike a solid planet like Earth, the sun is this giant ball of gas,
And because of that, it does something really weird. It actually spins faster at its equator than it does at its poles. This is called differential rotation, and what it does is it drags the sun's magnetic field lines along with it, twisting and tangling them up into these really complex knots of magnetic energy. So what happens when you get a tangled up mess of incredibly powerful magnetic fields? Well, you get weather. But we're not talking rain or snow here. This is solar weather, and it can be unbelievably violent. Probably the most famous feature of solar weather are sunspots. I'm sure you've all seen pictures of these dark little blemishes on the sun's surface. But have you ever wondered, why are they dark?
The answer is actually pretty surprising. Sunspots aren't really dark, and they're definitely not cold. I mean, at 4,000 Kelvin, they are still mind-bogglingly hot. They only look dark because the surface right next to them is even hotter, blazing away at around 5,800 Kelvin. So it's basically just a giant optical illusion caused by extreme temperatures.
And sunspots are really just the beginning. Those tangled magnetic fields we talked about, they can snap. And when they do, they can unleash these immense explosions of energy we call solar flares, or even launch massive clouds of charged particles out into space. A period with a lot of sunspots is called a solar maximum, and that's when the sun is at its most active and turbulent.
Okay, so why should we care about this, all the way here on Earth? Well, because when those particles the sun shoots out finally reach us, they interact with our planet's own magnetic field and atmosphere, and they create one of the most beautiful, spectacular sights in all of nature, the Aurora Borealis and the Aurora Australis, the northern and southern lights. That's right, the sun's weather creates our planet's greatest light show.
So for now, our sun is a stable, pretty middle-aged star. It's the steady engine of our entire solar system. But that hydrogen fuel in his core isn't going to last forever. So the final big question is, what happens when the tank starts to run low? Well, that story, The Death of a Star, is a tale for another time. Thanks for joining me.